quite match your notes to 102. You have 102 notes, but I did a lot of changing and doing tables and stuff on it, yeah? And I felt like that went pretty well. So this is what I'm changing it to. Now, I don't think you need to really write this down until I get to that slide. Then we'll start, you'll pick up your pencil and we'll go from there. So just kind of sit there and take it back in, and hopefully if you missed it the first day, then it'll make more sense now. The idea is to prove a limit is what it is. Now, I could, by direct substitution, see that that is 3. But remember, the only way we know that direct substitution would work is if we know it's continuous. And it's only continuous if the limit exists. So there's circular reasoning there. We talked about how we could get closer or put a window around the limit by using a table. If I put in 1, I would get 2.5 and 3.5. And from that, you might say the limit is 3. Now, to me, though, that would just say that you went 1 away from x. Here, you went 1 away from 2 and x. Now I'll come back to that in a second. That makes for a pretty tight window of 2.5 to 3.5 around y, but who's to say the limit has to be 3? There's a lot of numbers in here it could be. So you might argue that it's 3, but I could argue why not lots of other stuff? Why not 3 1/4 or all these other numbers? It's a pretty big window to just say it's 3. You with me? All right, I'll assume your silence means yes. Continue, Mr. Rickman. If you went a little closer then, you said, okay, that's too big a window for you to believe it, I'll go a little smaller. I'll get within 1/10 of 2 on either side. And when you do that, I think you'll get something like 2.95 and 3.05. Now, visually, that would mean if you got really close to 2, then you get a much smaller window around 3. And certainly you can see that that window around 3 is now excluding 3 1/4. 3 1/4 is out. There's a whole lot of numbers now that you said, I could have said before, that are out. So you might now say, well, surely now the limit is 3. And I could respond with, why not 2.97 or something like that. So you could keep getting closer and closer. In the case you went here, you might get 2.995 and 3.005. Now that's just a window of 5/1000ths away. That's a pretty tight window around. When I go that tight a window around 2, it results in a really tight window around 3, yeah? And you might say, surely that's good enough. I mean, look how small that window is. But I could keep saying, nope, still a lot of numbers in there. Now, the idea of delta epsilon proof, then, is the idea of making this ironclad theoretical proof. Now, just step back for a second in history here. Leibniz and Newton did their calculus, and it was awesome, huge, earth-shattering ideas. And it would be like a building with just bricks, with no mortar. It's great structure, but for something to stick for hundreds of years in math, it has to be proven. I mean, you have to be able to prove it. There can be no counter-argument that cannot be argued against. Now, the minute they came out with it, there's all these arguments from all over the place. Well, what about this? What about that? What about this? All these counter-arguments, and it wasn't really beefy mathematics-wise, So this French guy comes along, and he's kind of the guy that put the mortar between the bricks and made this calculus actually mathematically rigorous. Everything can be proven. And that guy, Cauchy, his name was, he's like the mason of the calculus, or he's the cleanup guy, he's the janitor of the calculus. He cleaned up all the messes that Newton and Leibniz made. This is his idea, okay? His idea was to say, all right, forget the table, forget the numbers. Let epsilon represent any closeness you want that it would take for you to believe that the limit is 3, okay? A trillionth, a billionth, whatever. Epsilon is some arbitrary closeness. Now, he said let epsilon be not a numerical, 5 thousandths away or 500ths away, but be any arbitrary number, however close you want, okay? I can prove that I can get the function. Now, the function is the green line and the limit is the dotted line, yeah? I can prove that that difference between those two is less than whatever number you want. Now, how close I demand, another way to say that is I can find a way to make this happen. The difference between the function and the limit, the gap, you can think of this as the gap here. This is that little gap, can be made arbitrarily close. All right? Now, when we did the table, or when I did the table, you didn't do anything, you just sat there. But when I did the table, I actually started with x, and the result was the y. This now, this is how close I needed to find an x to make that happen. That's delta. That's the how close I need to get to 2 to get an outcome that's as small as you want. The how close you need to get to x to 2 is delta. It's a lowercase delta, an unfinished 8. It's something like this. Now, the how close you need to get x to 2, that means the difference between x and 2 has to be less than some delta. And I can prove that if x is within that delta away from 2, that it must follow that y will be within however close you want of 3. Now, the absolute value is there because I don't care if it's above or below. I just want the gap to be the focus, not the over or underestimate. So the absolute value is just there to take care of the positive or negative part. Now, the idea then is this. This is the fancy pants definition of a limit. The limit is L if you can find that delta such that if I start within, I'm going to go visually, if I start within delta away from 2, it must follow that y's function, y's limits will be, y's values will be less than epsilon away from F. Now, in this table here, and I know you don't have the table, but here, that how close I got to 2, that's the delta. So in this case, delta was 1. And the result was I got a y closeness of a half. In this case, when I went to 1.9, the delta was 0.1. The result later then is the epsilon, or how close I got to the 3 value I expected, was 0.05. And later on, when delta was 0.01, epsilon was 0.005. You can see then that the delta and the epsilon are related, obviously, but they're not equal. Now, they're not equal because the slope of the line is not 1. If I had a line that was perfectly sloping at 1, then every inch gap here around x would result in an inch gap here around y. There would be perfect equality between the gap here and the gap there. But the minute this slopes steeper, I'm not very coordinated, sorry. The minute this slopes steeper, then a big gap around x results in an even bigger gap for y. But if this is flat, then a gap around x becomes a very small gap for y. So I think you'll agree that the gap in x relates inversely to the gap in y through the slope, yeah? The steeper the slope, then the smaller the result, or the bigger the gap. So in this case, you can see that the epsilon is always 1/2 of the delta, or I guess you could also say epsilon, or delta is twice epsilon. Now we usually go there because we start with x and go towards y. So the delta is what we usually start from. Generally speaking, delta is always epsilon over the absolute value of the slope. All right, now if so far that's probably saying pretty much what I said before. Let's try an actual what this is going to look like, and I'll say it again. The first time is just, okay, watch what I'm doing. By the third time, you say, I can do this no problem. I guarantee you, I think it's easy. All right? So the proof goes like this. And it is a proof. It's not a calculation. We're not doing a table. We're not doing a graph. It's a proof. And so you're trying to show that the definition of a limit is satisfied. The limit is L because the very definition of what a limit is has been satisfied. And it goes like this. You first identify, based on the slope, what's delta for this problem. In this case, delta, or how close I need to get around the 2, is epsilon over the slope's absolute value. In this case, epsilon over 1/2, or 2 epsilon, yeah? You then think of it like writing the theorem, or what you're going to prove. It's the thesis for your paper. Something like this. I will show that if x is close enough to 2, and by close enough to 2, I mean the difference between x and 2 is less than delta, then it must follow, as either I send it through the table or I send it through the graph and back towards the y, that it'll follow that y will be within an epsilon of the limit, or as close as you want me to get to the limit. Okay? That's, you could say, the thesis for your paper. Now the proof. You start by assume, or start with x, the x fact, the hypothesis. Assume that x minus 2 is within that gap you define. Okay. I want to now use your delta. In this case, we said that delta needs to be 2 epsilon. And that came from the fact that slope is 1/10. It's not always going to be 2 epsilon. Now you want to, through accepted algebra, make this f of x minus L is less than epsilon. Or in this case, we need to get to changing this to 1/2 x plus 2 minus 3 is less than epsilon. And we need to show that it must follow that the difference between y, which is the function, and the limit, which is 3, is less than that little arbitrary gap. So I'm going to have to do some arithmetic to this. Now, one thing I can do is I can get the epsilon by moving the 2 over. I can do that and not worry about switching the inequality because it's a positive number. Do you agree that mathematically I can divide both sides by 2? Yes? All right. Again, through accepted math. I want to get this 1/2 in here. Let's start by bringing in some absolute value. Isn't 1/2 the same as the absolute value of 1/2? Would you agree they're equal? Okay. We've talked a little bit in the sets leading up to it, but I'll say it again. It is an accepted truth that the product of 2 absolute values is the same as the absolute value of the product. The product of absolute values is equal to the absolute value of the product. It's going to be the same number either way, and it'll be positive, right? So this is the same as if I multiplied this in. Okay? When I went from that step to that step, I multiplied the 2 absolute values together. Now, the last part is a little bit of a creative step. I want to make this -1 into 2 minus 3. Well, there's absolutely no reason I can't rename -1, 2 minus 3. I think we'll all agree that -1 is equal to 2 minus 3. Yeah? Now I can substitute. What is 1/2 x plus 2? It is f of x. And 3 is the limit. And that is what I was supposed to prove, therefore. I guess you would read that as therefore. Okay? That is the idea. Now let's try one with the negative, which is a little trickier, but not much once you get some practice with it. All right? So we're going to start with our delta. You're going to identify for the reader. In this case, delta is epsilon over the absolute value of -3/2, or 2 epsilon over 3. Wait. Now for linear, that's always going to be the case. For curves, tomorrow, things are very complicated, and not always that case, because there is no limit. But don't worry about that tomorrow. For today, we'll enjoy the easy. All right. Now here's the idea. I will show that if the difference between x and, now it's not 2 like in the previous case because we're not approaching, x is not approaching 2 now. Now we're approaching 4. So if x, the difference between x and 4 is within this little gap delta, then it will follow, or it must follow, where it follows that y, or the function, the difference between y and the limit will be less than that arbitrary gap you demand epsilon, all right? In other words, I'm basically saying I'm going to prove that the definition of a limit is satisfied. Now let's assume we start with the assumption that x minus 4 is less than delta as our starting point, and we'll show that it must follow that f minus L is less than epsilon. What should I do next? Substitute in your delta. In this case, we say that delta is 2 epsilon over 3. Wait. All right. Now, we want to gradually work epsilon by itself and get this side to f stuff. So what should I do next? Multiply by 3/2. Wonderful. All right. Now here's where that absolute value and the negatives start to get tricky. Will you agree, will you stipulate that 3/2 is the same as the absolute value of -3? Would you agree those are equal? Okay. We also know that 2 absolute values can be multiplied together. So that gives me -3/2 x plus 6. Okay. Now what? This is the part where you have I'm trying to get f minus L. So it helps to think, well, if I want f minus L, then I want this, -3/2 x plus 7 minus 1, yeah? So now what do I do? Break the 6 up into plus 7 minus 1. Now we didn't break any math there. 6 is equal to 7 minus 1. Nobody's going to argue with this fact. But that serves the purpose of getting me my function. That's f of x, and that 1 is the limit. And that's what I was trying to show most happens. Now, if you were ever to try this, you think, oh, I'm sure it works out every time. Well, it doesn't work out every time. If I told you that the limit was 8, and you tried to run this, the whole thing would break down. Everything is not true. You get numbers that don't work. It doesn't flow like that. It just all breaks. Show it in a second, all right? So it does actually prove that the limit is what you say it is. It doesn't just always work no matter what you set up. Would you try one on your own, please? Okay. Sorry, in a minute. Very good. Roll. What did you let it delta equal? Okay, sounds good. So I will show that if x minus 1 is less than delta, then it must follow that f of x minus L is less than epsilon. If you start with x minus 1 is less than delta, then go x minus 1 is less than epsilon over 2. You can see why the absolute value definitely helps you because you don't have to switch the inequality. If you had negative 2 over there, you'd have to switch the inequality and the whole proof is bounders because then it would result in a gap bigger than. You should deal with the 2 by making an absolute value of negative 2, then bring it in, and then split the 2 into what you need to make f, which is 7, and what the limit is, which is 5. And that is f of x. Now, this will only work if you have the correct limit. If you said, for example, if you tried to prove that the limit is 4, the whole proof would be pretty much the same up to this point, but then when you went to break up the 2, you would try and argue that 2 is equal to 7 minus 4. Well, that's not it. Obviously, 2 is not equal to 7 minus 4, so you cannot make it true no matter how much you try if you have the wrong limit. It only proves the correct limit is the limit. All right, I want you to get one more of this. So, would you go to box 20 on set 103, which you'll be happy to see is a really large box, and replace 20 with, I don't know what it was to begin with, but would you do this in box 20? Okay, how's that proof going? Still working on it. Okay. Did you use the delta 3 epsilon. Okay? Does your thesis look something like if x minus 4 is less than delta, then it will follow that f minus L is less than epsilon. So let's start with x minus 4 is less than delta. And that means that x minus 4 is less than 3 epsilon, which means 1/3 x minus 4 is less than epsilon, which means the absolute value of negative 1/3. And the absolute value of x minus 4 is less than epsilon, which means the absolute value of negative 1/3 x plus 4/3 is less than epsilon, which implies that negative 1/3 x plus plus 2 minus 2/3, so plus 6/3 minus 2/3, yeah, that makes sense. Well, that's, I don't know if that step is necessary, I'm just an overachiever, but that is f of x minus x. Therefore, check. How'd that go? Good, okay. Yes.
Does it matter if you do, why do you, for like f of x minus L at the end? The very last one, why can't, does it matter if it's an L or if you did 2/3 for h? Isn't 2/3?
2/3, if you, instead of having an L here, you have the actual numerical limit, that's fine. As long as you, I guess, this statement and that statement should agree. You should prove what you said you were going to prove. And so if you have 2/3 here, you should have that. Okay, as long as it's exists. They're both accepted, yes. Okay, that said, let's talk